Okay, guys, we better get started for today. I'm going to try to pick up where you left off on Monday, and just go through some more seismology basics with you guys. So I guess we're going to start out here by just going over some general things about your survey. This is first slide here is probably a little bit of a review. So you have your source of some sort. And from your source, your energy is spreading out kind of spherically in all directions from that source point. Some of it's going directly to your geophones, like the green line there. Some of it's reflecting off of interfaces and coming back up to your receivers. And some of it could be refracting off of one of your interfaces. And so then at each geophone, basically, you're measuring a time series of those little vertical displacements. And that's coming in here as your trace. So this is what you're basically recording at each receiver. And you can basically stack up all of those traces, and you can put them into what would be called a common shot gather, which is this guy down here. And in there you can see here that you have your direct arrival coming in the red, in the green. And your shot is at 0, and then these are your offset distances from your source. And then you have your reflected arrival coming in here in the blue, and the refracted guy that's starting to come in there in red. So what are some things we need to think about when we're getting ready to do one of these seismic surveys? Well, we need to think about what type of sources and receivers we're using. We need to see, and those are going to be tailored to our application and what kind of data we're trying to collect and what we're trying to image. So really the source can be anything that kind of basically causes particles within the earth to move. So anything that we can put kind of an acoustic wave into the ground and get that to transmit. So they can be natural sources like earthquakes. They can be man-made sources like hammers, explosives, weight drops. And then for the receivers, we can use a seismometer, which is what we would use to record earthquakes. And those are basically like a 3-component device that measures ground displacement over a variety of different frequencies. Or they could be something like a little geophone, which you put into the ground. It has a little spike on it that you drive into the ground for a land-based survey. And that basically, most of those measure one component of the ground, just the vertical component of ground motion. They do have some that measure 3 components as well, but most of them are 1 component. So I guess here is just an example of one of your main natural source would be an earthquake. And these earthquakes can be caused from a variety of different things. They can be caused from like general plate tectonics, so you have an oceanic crust subducting beneath some continental crust. They can be caused, so that would be an example of kind of a thrust fault situation. Or they could be caused along mid-ocean ridges where you have extension and plates are pulling apart. Or like down in Southwest California where you have a strike slip fault and you kind of have a lateral displacement of these two plates against one another. They can also be caused by, they're often, when you have volcanic eruption, you're also going to have some earthquakes associated with that. And when you have a kind of lava traveling through the crust to come up to your magma chamber or something like that, you're going to have earthquakes that are associated with basically that lava moving through the ground. Some man-made sources, one of the most common ones that is used in industry is what's called a vibroseis truck. So this is basically just a giant truck that has this hydraulic system that lowers this kind of big pad down to the ground and actually kind of lifts the truck up. And then it can just basically vibrate that pad at kind of a sweep of different frequencies to put a whole, you can really kind of target exactly which frequencies you want to put into the ground. So if you're looking for something shallow and you need high resolution, you can put in kind of a higher frequency sweep. And if you needed to see deeper, you'd kind of extend that sweep into some lower frequencies. Because remember, your frequencies, the higher frequencies are attenuated more quickly, but have higher resolution extremely low frequencies. Another man-made source might just be explosives. And so those can be small explosives that are just buried shallow, or they can be fairly deep, large explosives that they put down into a borehole. In the ocean, we can also collect seismic data out in the ocean. So for that, they tow a streamer that has a series of air guns on it. These air guns basically are just, they just shoot like a bubble of compressed air, and then as the water kind of comes back in to fill that evacuated spot, it sends out a little shock wave that then goes down into the ground and will reflect and refract off of all of the layers under there. And so for that, you can have a single source, or like in this picture here, there's like 4 ships, and each one of them could have sources. So you could have a big, wide kind of sweep of data that you're collecting with sources in different locations. And then some of those ships are going to be, the receivers for those are going to be what they call hydrophones. So basically you're going to have like a big streamer that has these pressure sensors in it. And these pressure sensors are going to detect those arrivals of the waves due to the change in pressure in the water column that they cause. So lots of options there. Here's some small scale sources for use on land. They can be as simple as just a sledgehammer that's kind of attached to a timing device that will kind of tell your system exactly when the hammer hit like the metal plate that you're bringing it down onto. They make these guys here, which are kind of like, you put a shotgun shell in this basically, and then it takes the blast from the shotgun shell and transfers that energy down into the ground. They get a little bigger, like this guy here, which is just a weight drop. So basically they say like a little tower that has a pneumatic or a hydraulic cylinder in it. Hydraulic cylinder lifts up this big, heavy steel bar, and it has a hook on the end of it and kind of a giant rubber band stretched over the top of it. So as you pull that weight up, you stretch the rubber band or energy in the rubber band, and then the hook on the hydraulic cylinder will come off, and then you basically just fire that hard weight down onto the ground and send energy into the ground that way. Or like we've already talked about, you could use some small scale explosives. So then for the receivers on land, most of what is used are geophones. And so here in this middle diagram, we see kind of a cutaway of a geophone, and it's kind of showing you roughly how it works. You kind of have a little mass that is suspended on this spring, and this spring, or the mass and spring are kind of going through a little coil of wire. So any motion, any vertical motion of that mass hanging on the spring from the ground motion is then transferred into an electrical signal that is then kind of recorded and picked up on your kind of receiver box. So I guess you'll have a cable that has all of these little electrical takeouts on it right here, and so then you can connect your geophone to this takeout, and you can then kind of lay out your geophones kind of in a long line so that you have kind of your profile of receivers laid out. Again, in the ocean, you can use a hydrophone streamer. So this is just a picture of one of those giant hydrophone streamers where they have this big winch, and they can have some of these streamers are up to 12 kilometers in length. So some of them are very long. So they can collect huge amounts of data with those very quickly. For the natural sources and earthquakes and things like that, you'd oftentimes use one of these broadband seismometers. Like this guy here. So again, those just measure kind of like the 3 components of your motion, and they measure it over a very wide range of frequencies. And they're very sensitive instruments. Here's just a picture from Iceland, where I was doing some field work, and we had one of these guys buried here in the solar panel tower, and we were kind of using these seismometers to try to basically image magma that's coming in and filling a magma chamber underneath the volcano. Now I guess you can also just have a very simple seismometer just using your smartphone and the accelerometers that are built to that. They have apps for that. So if you ever want to play around with that for any reason, you definitely can. It can work as a rudimentary seismometer. So now we're going to move on, and we're going to look a little bit more about processing of the seismic refraction data. We've done a little bit of this already in lab this week. So like the simple case we worked a lot with in lab, where we had just kind of like our layers uniform layers, and the key thing there was that these layers needed to be kind of increasing in velocity. So the layer underneath it was faster than the layer above it in order to get our refraction event. So when that happens, we can create one of these time versus offset plots that look like this, just the one we're all used to here, and we can calculate the slope of the first layer off the direct arrivals. We can calculate the velocity of the second layer from the slope of this first refracted arrival, and we can calculate the velocity of the third layer from the slope of our refraction off of that second interface. But if things, I guess in all applications, we're not going to be guaranteed that we have this simple horizontal layer case where our velocity is always increasing with depth. So, I mean, refraction is kind of limited in its scope of use. We may have cases like this one where we have, or maybe layer 2 has a lower velocity than layer 1. So in that case, you're not going to get a refraction off of this first interface because, I mean, according to Snell's law, instead of that wave being refracted towards the interface and traveling along it as a critical refraction, it's going to actually be refracted towards the normal and just going to travel like more vertically downwards. So in that case, if this layer down here is faster, then you can get a refraction off of it, but you're not going to get a refraction and reflection off of it, but you're not going to get a refraction off this first layer. So we basically just have the direct arrival here, and then we have that refraction from the second interface here. So we wouldn't see any type of refracted arrival from that first interface. We can also have problems with basically layers that are just too thin for us to be able to detect with a refraction survey. So we can see over here, we just kind of systematically decrease the thickness of layer 2, and you basically see that the time at which that interface, that first interface, has the time at which we have a critical refraction from the first interface kind of decreases with the thickness of that layer. So here it's easy to detect kind of because we have a clear change in slope between that first refraction and the second one. But then here, as we decrease the thickness of that second layer, basically our intercept time for that second layer refraction kind of shifts, and the time at which we have a critical refraction from that first interface decreases until it's not really present at all, and we only really see the refraction from that second layer as a first arrival.
From the last slide, you always see the refracted arrival from the top of the third there if velocity greater than 2 but still less than 1, you're not going to see it. So.
Well, if so I mean, it would have to be, let's think about this. So as the energy is coming down, you could get a refraction along this interface if velocity 3 was greater than velocity 2. But then once that refracted energy starts to come back up, you could also then get a critical refraction across here, across this interface on the way back up, on the way for that energy coming back up. Some of it is going to be propagated through, probably. I think it would need to be greater than V1, but I'm not 100% sure about that. We'd have to check on that for you. That's a good question. Are people good with the general idea here on this slide? Yeah. And then instead of having flat-lying layers, we can also have dipping layers. So basically, when we have dipping layers, things are a little different. Because basically, so depending on if your shot is up dip or down dip, you're going to get different velocities out of it when you try to do your refraction analysis. Because kind of the path here that we see for the up-dip shot is longer than the path we would expect if it was a horizontal interface, right? So that dashed line would represent the horizontal interface that we would be expecting. And then since we're up dip of the shot, our actual red curve here is traveling a further distance than it would if that was a flat line interface. So since it's traveling a further distance, it's going to kind of underestimate the true velocity of that second layer because it's traveling a longer path than kind of what that standard refraction analysis would kind of anticipate. And then if we switch to the other end and we move our shot down here so that we have a down dip shot, which is then going up this way, this guy actually has a shorter path than anticipated because it was anticipating a flat layer at this location. And so this path is shorter than the anticipated one, so it's going to kind of overestimate the velocity of this shot. So then kind of what you're going to get at the end of the day, if you do an up dip shot and a down dip shot and plot them both together, you're going to have these two refraction events here, one from the up dip shot and one from the down dip shot. They're going to have different slopes. And one of them is going to be overestimating the velocity and the other one's going to be underestimating the velocity. But since the paths are ultimately the exact same path, they're both going to kind of have this same reciprocal time. So the overall time that it takes to get from source to receiver, if you just switch them and do the reciprocal, is the same. So that's good. I mean, that's a good check. Like everything's working out there. But these two slopes are just different because of the way we've analyzed the data. So I mean, we can work with that, and we can basically introduce this new angle gamma, which we kind of define as this little guy down here and use to get like the true dip of that layer. So we can then kind of figure out, we can kind of use the same basic analysis that we've used in the refraction for the horizontal layered case, and we can solve for what that dip angle is and the true depths to that slanted interface beneath the source and the receiver. So in addition to these dipping layers, you can also just have irregular layers, so like layers that are just bumpy, or maybe layers that have like a syncline or an anticline or something like that in them. And to deal with those, we're going to have to use some more sophisticated methods. Though these methods do exist, but we don't really have time to go through them right now. So we're just going to, there's a little bit of discussion on them in the GPT. So feel free to look there, but we're not going to spend any more time today kind of working through those. Let's see. So now we're going to kind of move on from seismic refraction and move on to reflection. So I mean, like refraction, seismic refraction is going to be very effective at finding interfaces and changes in velocity. And unlike refraction, we don't have to have an increase in velocity from the top layer to the bottom layer. So in that way, it's kind of more versatile. And we also don't have to only use the first arrivals like we were doing in the refraction studies either. We can kind of use, we'll see as we go through the processing that we can use kind of multiple arrivals and build up a good section. The image itself is going to be much more complicated that we get out, and the processing is also more complicated. But that's just kind of a trade-off that you have to deal with. So basically, when we're done processing, what we're hoping to have is kind of what we call a normal incident seismogram. So it's basically kind of a corrected record that we would have if we had a zero offset source and receiver, so that the energy was traveling straight down through the ground reflecting off interfaces and then coming straight back up to our receiver at the same point. After all of our processing, that's what we hope to have. So then that's just kind of how you should think about, that's what these images are comprised of, basically. It's just a collection of these zero offset or normal incident traces. Jesus. Skip. What is that? Sorry, guys. Okay, you can still see it up there. I don't have it on my screen anymore, but we're not gonna worry about it. We're gonna keep going. So this is just a section, like a seismic section. I don't mouse anymore, do we? Interesting. Holy cow. Don't have anything left anymore. What is it doing? Let me try getting this back here for a second. Hopefully we can get rid of it. There we go. I have no idea what that font was, but holy cow. I have no idea what's going on with that. So Was like I just plugged it in and it was fine. I guess I could go try to find an adapter for that. But by the time I do that, class is probably going to be almost over.
What? Okay.
Do you have this? Here too.
It's your computer. So this is just
Yeah. Yeah. Like I can't even get out of here. Like this thing is totally like something happened. Just totally frozen. Like I had a mouse a second. And now this totally frozen. It's in the Dropbox.
Did you send me it on Slack? Are you that? Okay. I think it's here. No, it's in here.
Just let me try to restart this guy, and I can just send it to you. Jesus.
Oh, that won't have anything.
No.
What am I looking for? Where's the lectures? Where's the lectures? I found it.
But I don't think they uploaded it for today.
Oh,
So I don't think that's going to do us any good. Hang on. We'll get there.
they did not.
There we go.
Oh, you got it.
No, that's not what I want. Need Slack.
You get it? I guess.
I mean, I have it here, yeah. Come on, Slack.
Or you can email it to me.
Here we go. Let's go. Where is it? It said upload.
Let's see if this works. Oh.
I had a UV C6. I didn't have.
Oh, it came off.
I don't know what's going on. Maybe one. Yeah, you can do.
Should we worry about trying to still keep recording this, Samantha, or should we just go? What do you think?
No problem. We just complained about.
Do we want to try to keep recording?
There's always like.
Okay, hopefully we can get through a little bit of this and it doesn't die on us again. So I guess with these refraction seismic images that we can build up kind of a volume like this, those little basically normal offset reflections. And we can see a great, like once we process the data, we can see a huge amount of detail in some of these sections. So we can see, this would be like a big thrust fault. So you kind of have this thrusting event here where you have this section of crust down here that's colliding with this section up here. And we have the thrust fault that forms along here, and portions of the accretionary wedge and this accretionary prism can be viewed down here. And we can kind of see like the reflector here off the oceanic crust, and then we have the sediments above it, and then the oceanic crust down here, and there's a strong kind of reflection off the top of that oceanic crust. Here's just another example, basically where this is a profile, and we can again see like a strong reflector here. It goes like that, and then that's just kind of interpreted as kind of at the base of these sediments that are up here above some bedrock, and you can see a number of different faults that are interpreted on it. But as we'll see, kind of determining the exact slope or dip of some of these faults is not always easy to do directly from the sections, and there's going to be some processing that we need to do to try to determine the accurate dips of those layers. So some of the main uses for seismic reflection. The biggest one is probably hydrocarbon exploration. So again, they can get very detailed images of the subsurface, and they can image quite deeply with this method. The refraction method was definitely a shallower method, mostly for geotechnical uses probably, I would say. For reflection, we can also use it for whole earth types of studies. So from earthquakes, you can use kind of reflections off of your different boundaries throughout the earth, like the MOHO reflector and ones off of the core, the outer core and the inner core, to whole earth types of studies or continental style studies. You may have heard of, I think it's EarthScope, which was a big kind of array of seismometers that was being put across the US. and they were just kind of moving them in waves across the US to try to get good coverage all the way across the states as they went. So that was a big study that was kind of doing some of that type of work. And they can also be used for smaller scale, like geotechnical problems or environmental problems. So again, they're good for kind of these non-uniform layers that don't have to be flat, and you don't have to have a specific velocity contrast between your top layer and the layers beneath it. So they're pretty versatile, but the processing is a little bit more involved. So if we go out and we collect some data, and we have one of our shots here at this point, like our shot is just, it's located right here, and you can see this is what we would call a common shot gather. So here we have like our this here would be kind of like the ground roll in the middle, and then we have some of our different reflections that are coming in here, and we can see basically that the energy is propagating outwards from the shot and arriving at the geophones kind of as it spreads out. So if we're going to try to convert this type of data into kind of those ideal seismographs or those zero offset traces, the first thing we're going to need to do kind of is we need to kind of understand kind of exactly what those traces are and what they're representing. So if we look at our layered earth here, we just kind of have a cross section of the earth here. We can draw a kind of 1D profile of the acoustic impedance, which is just the velocity times the density of each one of these units. So we can see how that acoustic impedance varies as a function of depth here. And then based on that, we can calculate a reflectivity series, which basically is just your reflection and transmission coefficients. It's built off of those. And so then basically we can build up one of these synthetic seismic traces by taking our source signature and convolving it with that reflectivity series. And as we do that, we see that kind of off of each one of these interfaces, we're getting a reflection. This here has been kind of spread out, so you can see the different reflections coming up. But just this is like a zero offset, so there shouldn't be any horizontal shift between the source and the receiver. So think about this as going down, but this has just been spread out so you can see it. And so you have these different reflections coming up back to the receiver, which is at the same location of the source, and kind of forming this seismic trace. So I guess when you're out in the field, you may have kind of your source here, and you may have an array of receivers, like geophones, set out, and then they may do kind of like what's called like a roll-along type of data collection, where you just systematically kind of move up the location of your source and all of your receivers. And by doing that, kind of sample a different portion of the ground and build up your profile that way. So when we go out in the field and we're collecting data, we're doing like a single shot. So we have a single source and we're collecting we're collecting data at a whole bunch of different receivers. So as we're trying to process the data and form one of these normal incident reflections or traces that we're going to put into the process section, first thing we need to do is make what we would call like a common midpoint gather, which is basically shown down here in this diagram. And so we're looking at all the different shots, and we're basically collecting the pairs of shots and receivers that share the same reflection point at depth. And we're putting all of those into like a shot gather instead of doing, or not a shot gather, but a gather of your traces. And so as we're kind of going through this, we can kind of think about the fold of a survey. And the fold is basically just how many times you've sampled kind of any given midpoint. So like these dots are offset just to show kind of each one of these represents kind of like a different move up of your source. So all of these guys are reflecting off of this first interface because there is only supposed to be one interface in this. But you can see that from source 1, as you go through it, you're going to sample these midpoints here. And then from source 2, you're going to sample basically what would be these midpoints here. So with this particular kind of survey setup, you're going to sample each one of your midpoints twice. So then the fold of the survey is 2. And this fold will be important later because basically we're going to be able to stack these measurements with a common midpoint to kind of decrease noise in our system. So this is just a kind of a summary of how we calculate the fold for a given survey. So with these reflections, we also need to kind of think about the fact that the reflected arrivals on our time versus offset plots show up as a hyperbola instead of just like a linear arrival. And so then the travel time of that reflection is given by this equation here. So when we look at this guy here, which is just basically, this is going to be one of our common midpoint gathers. And so here we're plotting kind of the offset of your source and receiver as a function of your reflection time. And you can see that we kind of have a hyperbola shaped change in our curve here. And so what we're going to try to do next is what's called a normal move-out correction, which is basically accounting for this difference in time that we see in our arrivals, which is just purely due to the increased offset that we're seeing between our source and receiver. It has nothing to do with the reflector that this is coming off of, because the reflector at this point we're still assuming to be horizontal. So basically we just need to fit a hyperbola to those reflections, and we can calculate kind of what the time difference is supposed to be at each of those. So here we have those reflections coming through here, and we can choose a series of different velocities, pick like what we think the intercept time would be, and then we can choose a series of different velocities, calculate these kind of best fitting hyperbolas that go through it until we find one that kind of fits nicely through it, and then that that velocity that fits best is kind of just what we would call our stacking velocity. And so you can also, if you want to, one way of kind of automating that picking program of which is the best fitting velocity, you can kind of sum the energy kind of along each one of these hyperbolas, and then the one with kind of the peak energy is going to be the one that is fitting those arrivals the best, if that makes sense. So then this is just kind of another way of doing kind of the same thing, except you're kind of doing that integration over a huge sweep of intercept times and velocities. So you're making like a full 2D map of intercept times and velocities, and you're going to have this point where your energy focuses, and that's going to kind of tell you where your best fitting intercept and your best fitting velocity for that particular reflector is. And so this type of analysis is called semblance analysis, and it's a very common way of trying to pick those kind of best fitting stacking velocities and intercept times. So then this kind of just shows what the NMO correction does. Once we have kind of found this best fitting hyperbola, we can then calculate our delta t's and subtract those off of these other traces so that we basically flatten that reflector. And so then that has essentially taken it from kind of these, that has essentially turned it into kind of this normal incident reflection, which is now going straight down and coming straight back up. So we've taken out the geometry effects of the longer travel times for the measurements with the larger offsets. And we now have a flat line reflector in the final image here. So here's just kind of an example of it. Here's our original common midpoint gathers, where you can see you have probably your direct arrival coming in here, and then we have a pretty clear reflection coming in here. And then after we've done the NMO correction and found that kind of best fitting velocity, well, actually here they've done it for 3 different velocities and they're showing it. And so one of them here, they've kind of underestimated the velocity, so that reflector is not showing up as being flat lying. It's kind of curving up. Here is the one that's kind of balanced things nicely and picked a well-fitting velocity, and it's pretty flat lying. And then here's one where they've selected a velocity that's a little too high, and so then that reflector is actually dipping upwards here. Yeah. So then this is just kind of a summary of that whole kind of process. We're kind of displaying our original traces here in our common midpoint gather. We're maybe getting rid of bad noisy traces, and then we're kind of picking kind of like our first arrivals. We're kind of fitting a hyperbola that goes through all of those to find kind of our stacking velocity. Then we're using that stacking velocity to account for the different travel paths for those different reflections to turn them into kind of normal incident reflections, which are going straight down and coming back up. And then once we've kind of lined all of those guys up from a given common midpoint, we can basically sum them, which is the stacking process. So we take all of these traces and we kind of stack them together. And that stacking together kind of amplifies the point at which we have our reflection and the energy. And the other parts of it kind of, since it should just be random noise and most of those other points, it kind of cancels out. So you have a strengthening of your signal right at the reflection and kind of hopefully a canceling of your noise in the other locations. So then you get a nice crisp reflection. And you can do other things with it, like increase the gain and things like that. But then mostly you do this for each of your common midpoints and you combine them into an overall section, and then you can kind of interpret the section to see offsets, like such as a fault or something in your interface. So yes, I guess this is just another example. We had here this common shot gather in this panel here. We converted that into a common midpoint gather for location 27, which would have just been the spot where all of our data that had a reflection at location 27. And then we would calculate our NMO correction for this, find that stacking velocity so that it kind of made that reflection a horizontal layer. We would stack all of those traces, and then those would become one single trace in our section that we were looking at the end. So that's kind of the general flow of that. I think we're going to leave it there for today, because I think it's pretty much time to go, isn't it? Yeah. And we'll pick up with migration and a few other processing techniques on Friday.